For nearly a century, this wall of concrete has held back one of the largest reservoirs in the United States. It helped power the rise of the American Southwest, controlled a violent river, and became one of the most recognizable engineering projects on Earth. Yet today, Hoover Dam faces a problem its original builders could never fully solve. The dam itself is still standing. The water behind it is disappearing. And if Lake Mead falls far enough, the enormous generators buried beneath Hoover Dam could eventually lose the force they need to produce electricity. To understand how a machine this massive became vulnerable to something as simple as a falling waterline, you have to go back to the river engineers once considered almost impossible to control. Before Hoover Dam, the Colorado River could be brutal. It crossed deserts, carved enormous canyons, flooded farmland, and carried precious water through one of the driest regions in North America. Cities and farms wanted that water. They also wanted protection from it. So engineers proposed something extraordinary. Instead of adapting to the river, they would build a structure powerful enough to control it. The location was Black Canyon, a narrow gorge between Nevada and Arizona. Here, towering rock walls created the perfect place for an enormous concrete barrier. The plan was to construct an arch-gravity dam more than 700 feet tall, creating a reservoir behind it that would eventually stretch for more than 100 miles. There was only one obvious problem. The Colorado River was flowing directly through the construction site. Before workers could build the dam, they first had to move the river itself. Crews attacked the canyon walls with explosives and pneumatic drills, carving 4 gigantic diversion tunnels through solid rock. Each finished tunnel was roughly 50 feet across. Together, they created an artificial route around the future dam site. In November 1932, the Colorado was finally forced into those tunnels. For the first time, workers could reach the riverbed. What they found created another problem. A structure weighing millions of tons could not simply sit on loose sediment. Crews excavated enormous quantities of mud, gravel, and rock until they reached a foundation strong enough to carry the dam. Meanwhile, workers known as high scalers hung from ropes hundreds of feet above the canyon floor, blasting unstable rock from the cliffs. One mistake could send them falling into the canyon. Yet even after the site was cleared, engineers faced a challenge hidden inside the material they planned to use. Concrete gets hot as it cures. For an ordinary building, that is manageable. Hoover Dam was different. Engineers calculated that if its enormous concrete mass had been poured as one continuous structure, the interior could have taken around 125 years to cool naturally. Worse, uneven cooling could create stresses, cracks, and potentially weaken the entire dam. So they effectively built it like an enormous puzzle. Instead of one giant pour, Hoover Dam rose as hundreds of individual concrete blocks. Inside them, workers embedded an astonishing network of thin steel pipes. Cold water was pumped through these pipes, pulling heat from the curing concrete far faster than nature could. More than 500 miles of cooling pipe were buried inside the structure. Once the blocks cooled and contracted, gaps between them were filled with grout, locking the pieces together into one gigantic mass. By 1935, the canyon had been transformed. A curved concrete wall now towered above the Colorado River, roughly as high as a 60-story building. Behind it, water began spreading into the desert, creating Lake Mead. Yet stopping the river was only half of Hoover Dam's purpose. The real machine was hidden below. Water from Lake Mead enters massive intake towers and travels downward through huge pipes called penstocks. As gravity accelerates the water, it reaches turbines inside the powerhouse at the bottom of the canyon. The rushing water spins those turbines. Generators convert that rotation into electricity, and transmission lines carry the power outward. At full rated capacity, Hoover's power plant is capable of producing roughly 2 gigawatts. The concept sounds simple. Water falls, turbines spin, electricity appears. Yet there is one detail that changes everything. The amount of electricity Hoover Dam can produce depends heavily on how high the water sits above those turbines. That vertical difference is called hydraulic head. More water above the powerhouse means more pressure and more energy available as the water falls, which means the reservoir is not simply storing water. Its height is part of the power plant. For decades, Lake Mead rose behind Hoover Dam until the white cliffs surrounding the reservoir were largely hidden beneath water. At high levels, the lake became an enormous reserve serving cities, farms, and industries across the Southwest. Then the system began changing. Long-term drought, rising temperatures, and enormous demand across the Colorado River basin pushed Lake Mead downward. As the reservoir shrank, pale mineral deposits appeared across the canyon walls. The famous white bathtub ring became a visible measurement of missing water. Marinas had to move. Boat ramps reached dry ground. Islands and rock formations emerged where water once stood. For tourists, it looked dramatic. For Hoover Dam's engineers, it represented something much more serious. Every foot the reservoir falls reduces the hydraulic head pushing water toward the turbines. The dam may still look enormous from downstream, yet its generating ability can decline because the invisible column of water powering it has become shorter. And eventually, there is a limit. Hoover Dam's original equipment was designed for a much fuller reservoir. Engineers later installed wide-head turbines that allow the power plant to operate efficiently across a broader range of water levels, extending generation capability to much lower elevations than before. That bought Hoover Dam something incredibly valuable: time. But it did not eliminate the fundamental problem. Around an elevation of 950 feet above sea level, Lake Mead approaches what is commonly called Hoover Dam's minimum power pool. Below roughly this level, generating electricity through the turbines becomes extremely difficult or impossible under the current system. And there is an even darker threshold below that: dead pool. At roughly 895 feet, the reservoir would be so low that water could no longer flow downstream through the dam by gravity through the normal outlet system. Hoover Dam would still exist. Lake Mead would still contain water. Yet the system that transformed the Colorado River could no longer operate in anything like the way it was designed to. That possibility creates a strange engineering paradox. In the 1930s, builders fought to survive extreme heat. Falling rock, dangerous tunnels, enormous machinery, and a river powerful enough to destroy their construction site. They moved millions of cubic yards of material, poured millions of cubic yards of concrete, and finished one of the most ambitious structures of its era. Nearly a century later, the greatest threat is not the river being too powerful. It is the possibility of there not being enough river. Still, Hoover Dam is not simply waiting for failure. Newer turbine technology has already expanded the range of water levels at which electricity can be generated. Water managers coordinate releases throughout the Colorado River system, while states, cities, farmers, and the federal government continue negotiating how a shrinking supply should be divided. Every decision matters because Lake Mead is connected to something much larger than the dam itself. This reservoir is part of a system supporting tens of millions of people across the Southwest and Mexico. Its water irrigates farmland, feeds major cities, and passes through infrastructure built around assumptions made generations ago. Hoover Dam, therefore, represents something bigger than a power shortage. It is a giant physical gauge for the Colorado River. When Lake Mead rises, the system gains breathing room. When it falls, the bathtub ring becomes a warning visible from miles away. Perhaps that is what makes Hoover Dam so remarkable today. The engineers who built it solved problems that seemed almost absurd in the 1930s. They rerouted a river through mountains. They invented ways to cool an unprecedented mass of concrete. They lowered gigantic machinery into a desert canyon and turned falling water into electricity on a scale few projects had achieved before. Their machine worked almost too well. It helped make massive growth in the desert possible, while the reservoir behind it became one of the most important stores of water in the American West. Now the engineering challenge has reversed. The question is no longer whether humans can build something powerful enough to control the Colorado River. It is whether the Colorado River will continue carrying enough water to power the machine built to control it. Because Hoover Dam does not need to crack, collapse, or disappear to lose its power. All that has to happen is for the water to stop reaching it.